So with this then, all right, so welcome everyone. Thanks again for joining us for the next in our webinar series in getting data science into the physics curriculum. So thank you for attending. Today we have two dynamic lectures. One will be Matt Bellis and the other will be Amy Roberts. And so we'll start with Amy. So Amy is now at UC Denver, University of Colorado at Denver, and her research focuses on understanding energy dispersion on low threshold detectors and building software solutions that solve common data, software, and analysis problems for the nuclear physics community and broader communities that also depend on data. And so she's going to tell us a bit about her efforts in getting data science into the physics curriculum. And I'll introduce Matt once he begins his portion. So Amy, we're really looking forward to what you have to say. And just as one small note before Amy begins, we will be having a workshop on data science education next month in June in College Park, and we'll be posting a little bit of information about that in the chat. So without further ado, Amy.
Awesome, thank you. So I apologize in advance that my computer won't, the share screen function isn't quite working in Zoom. Could I maybe ask someone to click on that link and share their screen? I promise there are not many slides, so it will be short.
Okay, let's see if I'm capable of doing this.
Awesome, thank you.
Okay. It's nice that you had this on. It's nice that you have this as a Google webinar. So let me share my screen, and we'll try and do the dangerous thing of just sharing this particular application.
Thank you
All
so
right.
much.
And then hopefully you can see the screen.
Yes.
And so then are you able to see this as a slideshow now?
I am. Thank you. This is perfect.
Okay, so just tell me to advance to the next slide and I will.
Awesome. Thank you so much. I really appreciate it. Okay, so I wanted to say a little bit more about my research background and kind of explain what my perspective on computing is. So by training, I'm an experimental nuclear physicist, and really with an emphasis on the experimental. So I did my PhD work at the University of Notre Dame, which has sort of one of the few tandem accelerator facilities in the nation, where you can really do everything from nuts to bolts, all the way down to your science results. And so that's a really exciting environment. So it's very lab centered. And so in that environment, I was the one who always maintained the computer systems and did a lot of the computing, but really my focus was on experimental science. And since then, I've really moved to be entirely in the software and computing realm. So I kind of had made a very conscious decision to do that at one point. So my experience was that that the sexism in the lab was just, it was very difficult, not necessarily difficult, but very time consuming to deal with. And I kind of just had one of those days where I was like, well, I don't want to spend 50% of my time as a physicist managing people's expectations of me and figuring out how to be safe in the lab, right? Like in an experimental setting, when people don't treat you as a colleague, it can, like you work with stuff in physics labs that is hazardous, and you really need everyone like kind of on the same page and focused. And when you're dealing with additional stuff beyond that, it can get kind of dangerous. So I really felt like computing gave me a lot more control over my environment, and that sexism would be more manageable. And I would say that suspicion has really borne out. I've really had a great time focusing on computing and software. Um, and then the primary focus right now for me is sort of the software infrastructure that specifically makes physics analysis really accessible. And so my interest there is in creating systems that don't require a lot of secret knowledge. Ideally, I would like to make physics analysis ecosystems that don't require any secret knowledge. So that's the goal. We're getting there. But just really reducing that you have to talk to the right person to get the right information, and you have to know all the secret people that you need to talk to get the information you need to just look at the data and analyze the data. So that's a real interest of mine, and I am really excited about a lot of these sort of national infrastructure programs that have made that possible. So thank you, Exceed. Yeah, I don't know. I'm sad that it's changing its name to Access. So I don't know if anyone has any ideas about Exceed tattoo designs. Let me know. I feel like it should be commemorated because it's a great resource. Okay, so that's me. And the main point here is just that computing is really essential to the type of science that I do. So I'm a PI in a dark matter search, and the data that we collect is data that pretty much has to be analyzed, not necessarily in an HPC environment, but often in an HPC environment. And certainly the simulations that we do for that system have to be done in an HPC environment. And I think that there is just a lot of value in making really good computing systems that are really usable for people. So that's kind of my bias, is that everyone should learn computing because it's an essential part of being a physicist in the modern age. So that's sort of where I'm coming from. Okay, so that's me. Let's take a look at the next slide. Okay, so then here I am in my teaching environment. So CU Denver is it's not a primarily undergraduate institution. It actually is technically an R1 institution. However, the physics department does not have a master's program or a PhD program. So we are an undergraduate only physics program. So that's really interesting. It means that the undergraduate students get really heavily involved in research, which is great. Yeah, we have a lot of fun. So right now I am teaching calculus-based physics 2. That typically has 50 to 70 students in it. And then I teach upper division electricity and magnetism, which is much smaller. And so that typically has 7 to 12 students. So that's kind of the typical classroom size that we're looking at. And the other thing that I wanted to mention is that in terms of incorporating computing into my curriculum, I have a lot of freedom. So my particular interest is really on focusing at students understanding how physicists approach things. So sort of that idea of there's a few fundamental laws and everything flows from those. So that is sort of what I mean by that physics approach. I'm really interested in students having a good time. I don't know if I'm allowed to say this out loud. We're recording this, so it's going on tape. So whatever, this is my focus. If anyone disagrees, I'm happy to talk more with you. But I think, especially for an intro physics class, one of my goals is for students to have fun. And I really like to see and sort of create an environment where students can develop a really strong sense of belonging with their peers, a strong sense of themselves as scientists. And then the other thing that I'm really interested in is on identifying skills that I think will really help students succeed in their future education and their careers. So I think it's pretty clear how computing fits into this. All of the students that are in my classroom have classes that assume they have computing knowledge. But when they come to me, even if they're fairly advanced, they haven't necessarily had any computing before. So yeah, so I'm going to talk a little bit more about this in the next slide, but it's an environment where students are often very interested in learning about computing, but don't necessarily have any background in computing. Okay, so then sort of some caveats. So I think that, it's really important when I'm talking about the things that I'm doing in my classroom to keep in mind some of the freedom that I have. So right now, my department doesn't have any content guidelines for courses. So I can do whatever I want as long as I can reasonably fit into the course description that's on our registration website. I'm okay. So I have just a lot of freedom in terms of content that I can focus on. Content that I can omit is really important because, of course, we spend time actually doing computing in the classroom, and that means we have to cut some stuff, or it means I cut some stuff. The other thing I want to mention is that my students are on average a little bit older. So the fact that they're coming into a physics class that has no computing prerequisites, and I'm saying you're going to be doing computing for some of this class, they're pretty willing to roll with the punches. And I tell them why. I think this will be valuable for your future classes. These classes are going to require that you're proficient in computing, and this is a good place to get started in a low stakes environment where all of the other thing I do is all of the computing that students do is effort only. Effort, put in a little bit of effort, and you will get full credit for it. So it's sort of a very low stakes environment for students to start playing around with computing if they're interested in it. And so all of that really makes for an environment where it's really straightforward to incorporate computing into the classroom. Anyway, so I just kind of wanted to mention that that's the environment that I'm working in. Okay, so let's take a look at what I actually do. So next slide and last, I promise. Okay, great. So what do I actually do that's computing in my physics classroom? And this actually applies to a significant extent to electricity and magnetism. And I'm happy to talk more about that if people are interested. But the fundamental thing that I do here is in physics 2, students have sort of standard homework sets. And what I have is I have a guide for every single homework problem in their standard homework set. So there's a link there, which you guys can click on if you're interested in checking it out. And what this guide does is it talks to the student about the problem. And it also includes instructions for building a solution in Python. And if you are taking a look at this, I linked to a problem that has an actual semi-decent guide built out. They're not all that good. That's something that I'm continuing to work on. But the idea is for this system to basically be like Chegg, but better. So what I want to say here is that this was really a leap of faith. So what this idea of basically giving the students the answers to the homework problems, we found that a lot of students were really struggling with figuring out where to start with problems. They were looking at online resources like Chegg and getting really confused, and the information that they were looking at wasn't always good. And I kind of felt like, I feel like the students are trying to tell me that they don't quite have the tools to do these problems. And on the one hand, I kind of feel like they need to figure it out. And on the other hand, I sort of wondered, what would happen if we made something like Chegg, but it were better, right? Or we're a little bit more focused on the particular concepts that I'm trying to teach them in class. Right. And so then we also had this idea of incorporating specific material to help them build a program for it. The original idea behind having students build a program was that I thought that some of the students had a really good sense of using variables to represent quantities, right? And a lot of the students just plugged numbers directly into their calculator, and they had, when we would talk to them about how they were trying to approach a problem, it would be this very confused description of, what they tried to plug in. And I'd be looking at, I'd be looking at their like TI-82 screen and trying to figure out what was going wrong. And so I originally started having students do a little bit of programming in class as a way to help them develop this idea of the power of representing numbers with variables. So that was how it kind of started. And then some of the students I found actually found that thinking about how to write a program helped them understand the material in a way that they didn't when they were just doing it on pen and paper. Not all of the students, but some of the students. So that was kind of the seed of this idea. And then we came up with this sort of parallel idea of maybe we should just have a guide that tells the students how to do these problems, since that's what they want. Let's just see what happens if we do that and see if it helps or if it's awful, or just see what happens. And so what we came up with was the idea of sort of fusing the programming with the guide. So the idea here is that we provide them very specific instructions on how to write the program, and then we really reward them for doing any kind of engagement with that. So, and we also sort of make incentives for that. So the incentives are, so we tell them how to do the program. If they write the program, then they have a program that gives them the solutions to all of their homework problems. And so we actually have 2 identical homework sets that they do that use random numbers. So one of them is due a little bit early. And so if they spend time on that and write their programs, then their programs automatically give them the answers to the second homework set that's due a little bit later. So they get extra credit for the early bird. We call them the early bird homework problems. And then the other is just their regular homework, but they have hopefully written a program. So the idea is to sort of give them strong incentive to write some kind of program. Usually what we have in the guide is Python, but we also really work with them on spreadsheets. So we have some students doing work in Python and some students doing work in spreadsheets, and some students find the programming aspect really stressful and skip it altogether. And so then they're sort of like rewarded with a program that makes it very easy for them to do this sort of double homework problem structure. The other thing that they do is their pre-class reading assignments are all based on these guides and trying to write a program that does a particular homework problem. So again, we just really want to make engaging with the problem and engaging with the problem with code really valuable for the students. So that's kind of the goal here. And then the final thing that we do to encourage them is that exams are very project-based and they're completely open resource, and students can actually submit code that's well commented as an exam project and get full credit for that if they meet, a set of criteria. So yeah, so I guess I would say that this has been interesting. There have been all kinds of benefits and all kinds of things that aren't working too well. But I'll maybe save that for the questions. Yeah, that's me, and I'll hand this over to Matt. Thank you very much.
Okay, so thank you very much for that, Amy. And we'll have some more questions for you after Matt's presentation. And there's just a little note in the chat that we'll use Slido for Q&A. And so that link has also been put in the chat. And we'll ask you some questions about what you've just discussed, as well as some of the specifics with data science. So let me stop sharing. And all right, so let me just close that. And so our next speaker is Matt Bellis. And Matt comes to us from Siena. And so he's a particle physicist. And I'm really curious to see what he's been doing with getting data science into the physics curriculum. So Matt, looking forward to hearing what you have to say. Huh. Okay, I'm a little worried. I saw Matt just re-entered the Zoom, and he looks kind of frozen. Are you there, Matt? Okay, so Matt, feel free to start. I just introduced you. I think maybe we lost your introduction, or you didn't hear it as you were trying to reconnect. Uh-oh, he's not able to unmute. So meanwhile, then why don't we ask a quick question of Amy, which is what kind of computing? Okay, Matt's back. Let's just try one more time. So let's see, Matt, are you able to unmute?
Yes, can you hear me now?
Ah, yeah, perfect.
Oh my
All right.
gosh.
We conquered you again, right?
So embarrassing. Oh my God.
No worries. Happens all the time.
Right, right,
All
right.
right. So
Uh,
looking forward to hearing from you. Let's
Great.
leap right in.
Okay, thank you. So before I share my slides, I just want to kind of acknowledge something. I have an 8-year-old son, and the tragedy in Texas has rocked me, and it's very possible it's rocked some of you, whether you have children or not. And so I kind of want to just take a moment to acknowledge that our heads might all be in different spaces right now. We're here for this meeting to discuss our professional work, but I'm just kind of want to recognize that we might have other things on our mind. And since this is a data science meeting, I think over the next few weeks and months, you're going to be seeing a lot of charts and statistics and narratives that have been constructed by data scientists. And so in some sense, we are part of the discussion which is taking place, at least in the tools that we can provide. So before I go and talk about the physics centered, I kind of just wanted to acknowledge what's happening in society right now. Okay, so I appreciate everybody allowing me to recognize that. So and now, and I think I need to have screen sharing enabled for me. It says it's host has disabled participant sharing. Oh, now I can. Thank you very much. All right. So I have some slides here, and I can't really see everybody. So can someone let me know if you can see my slides?
It's perfect.
Great. Thank you very much. All right. So I've got about 20 minutes of slides, and then I'm very much looking forward to the discussion. And I want to thank Amy for taking the time to explain all the stuff that she's doing. It's really interesting and fascinating what we're all working on, and I'm excited to kind of be inspired by this discussion. So let me jump right in and tell you where I'm at. I'm at Siena College. Not everybody is aware of us. We're an undergraduate-only institution in upstate New York. We're located just outside of Albany. This is about 2.5-hour train ride north of New York City. Again, we have no graduate students. We have about 3,000 undergrads. This is where we're located. We are a Franciscan college. So we have friars on campus that teach some of the classes. You are not required to be Catholic to go here, but that's the history. We have a strong school of liberal arts and a school of business, and we have quite a strong school of science with a pretty active research group. Most of our class sizes are between 15 and 24. We have smaller classes. I've taught classes as small as 6, and sometimes they go up to about 30, but you're actually kind of constrained by the size of the classrooms. And this will play into some of my discussions. So I came to Siena about 2012 in the Department of Physics and Astronomy. We have a vanilla physics major, or as I call it, a universal physics major. We now have an applied physics program with both a mechanical and electrical track. And then we just recently started an astrophysics major. The applied physics major just launched about 5 years ago, the astrophysics major about 1.5 years ago. And in 2013, I joined the CMS experiment. This is one of the experiments at the Large Hadron Collider. Prior to that, I was a particle physics researcher doing work with the Babar experiment at SLAC out at Stanford. And before that, at Jefferson Lab in Newport News. I've also done some work in some direct detection experiments with dark matter and some cosmological work that's primarily computational. And in January of 2022, this year, I became the coordinator for our data science program. So even though I'm in the Department of Physics and Astronomy, I now have this extra role. And this is just to acknowledge that I receive funding from the NSF for my work with the large CMS, which is mostly computational. I don't really build any of the equipment or contribute to that, but I do work on a number of computational fronts in addition to the analysis. And this informs what I do with students as well as in the classroom. Now, I'm going to talk to you mostly about my involvement with teaching, but I want to acknowledge some of my colleagues. This is not all of them, but they are doing work which is data science adjacent. And this informs their work in the classroom as well as the research. So one of my colleagues, John Moustakis, he does astrophysics work with the DESI experiment. This is the Dark Energy Spectroscopic Instrument. He does quite a bit of machine learning in his work. Michelle McColgan does physics education research and often has to analyze data sets of our students. Graziano Vernizzi is a computational physicist, works with primarily nanoscale techniques, so much of his work is all computational with our students. And Rose Finn also does astrophysics, where when she teaches observational astronomy, there's usually quite a large component of it which is computational based. Now, in putting these slides together, I really had to think about like, well, what do we mean by data science? And this is different things to different people. And I hope you'll forgive me. You know, I teach a lot of undergrads. And so, you know, the memes are the way to get them paying attention. And so, you know, sometimes physics students are like, oh, I'm doing a line fit. This must be data science. And then other people are like, well, physics is data science, right? And like, no, physics plus Python is data science, which I have some issues with this idea. And I'll discuss them in a second. And if you're unfamiliar with the memes or if it's too cringy for you, I apologize in advance because there will be more coming along. So again, if I'm going to talk about how we have data science in the physics curriculum, I've got to at least comment on what data science is about. And this is a standard infographic that I've seen a number of places. This idea that data science exists at the intersection of math and statistics, computer science, and then domain, you know, whatever the domain knowledge is in what you're working with. And it's, you know, there's no real science in this infographic. And so you've got to think about, well, what is science? And I tend to think of it as applying the scientific method to solve some problems. You know, sometimes I make these snarky jokes with my colleagues, like, well, what do you mean data science? Like, how are you doing science without data in the first place? This seems kind of a little bit redundant. But I think data science is really referring to certain skills and tools which are becoming almost semi-standard, certain statistical approaches, certain discussions about inference, and of course, there are the computational tools that people are using, or even data gathering. And so are these skills and tools data science? Is that what we mean by data science? And I'm not sure, but again, maybe kind of like talking about this is a good starting point. Now, we've had data science at Siena even before we had a data science program. So historically, and this is prior to fall 2017, we had a number of faculty doing data intensive research. And so we had students that would work with us on projects that they found interesting, and these were often not directly our research, but more computational or data science. So Sarah Mahar worked with me for a few years analyzing data with this community partner who disperses resources for homelessness and homelessness prevention. Spencer worked with me for a few years doing a lot of sports analytics as well as on the homelessness data. Ben as well, this is them at the Sloan Sports Analytics Conference at MIT. We submitted a paper that made it past the first round, but not the second. But they still got to attend the conference. And Sarah went on to get an MS in data science, even though her undergraduate degree was in physics. And as part of this effort, because we had all these students doing computational work, in 2015, I created a course called Computational Tools for Physicists for Freshmen. And this replaced an intro programming course that had been taught out of our CS department. And so the idea was that I would teach them Python, but we would also spend about a week and a half on LaTeX. I would show them the Linux command line, and then we would talk about version control, Git, and GitHub. But the majority of it was kind of teaching them Python. So this was 2015. And then in 2017, we launched a data science program where you can get a bachelor's in pure data science, applied data science, which has just a little bit less of some of the background computational classes, and then a minor in data science. And now this is separate from our business analytics course, and that's a whole other discussion. But at Siena, you can do both business analytics out of our School of Business and then data science out of our School of Science. It's an interdisciplinary program. There's a faculty steering committee made up of, it's 2 colleagues from CS, 3 from math, 2 from physics, 1 from environmental science, and 1 from philosophy, but because we require all of our majors to take an ethics course. And this is either our standard ethics course, or we have one that is more tailored to technology, science and technology issues. This was not, when I said those numbers, that's not, by design. We didn't require 2 and then 3. These are just the people who were interested and wanted to get involved. But we have about 9 members that are on the steering committee. And when we were developing the curriculum, we really talked about the idea that the emphasis would be in the curriculum about hands-on experiences with real data whenever possible. Okay, so where do physics majors meet these this data science experience, either in the tools of skills? And I would entirely accept the argument that every physics major does data science, because at some point you're taking some sort of data, ideally, and you're analyzing it to tell a story or test a hypothesis. And what is that if not data science? But let's get a little bit more specific. So in our genphys 1 and 2 program, so these are freshman physics majors, they see Python in the labs from day 1. And this has been since about 2013 when I first got here. We would install Jupyter notebooks on all of the computers, the laptops that they use, but now we use mostly the Colab environment with the Jupyter notebooks that are hosted by Google. A few years ago, I worked with some colleagues to make our labs more inquiry-based. I won't go into the details of this as much, but just comment on there's a movement in physics education research to make Gen Phys labs less cookie cutter and more open-ended. So students are coming up with either their own questions, or they come up with how to design the experiment to test those questions. There's quite a bit of frustration sometimes from the students because it's open-ended, but this is kind of like more how real data science is. We have emphasized the discussions about uncertainties. Students are not allowed to use the word error because we talk about uncertainties. And you could argue that this is really starting to dip our toes into what people talk about the more formalized statistics that's used in data science. And depending on who's teaching, at least what I will do is if I'm talking about line fitting, I really discuss this in terms of hypothesis testing. You are testing to see whether or not your data is described by some model, which might be a linear fit or a quadratic. And again, this gives you kind of access to the language that's used in data science. And I would argue that the language really matters when you're trying to introduce these ideas. So those are our freshmen, but besides that, the freshmen get dumped into a class which is also the intro course for our data science majors. And this class is called Exploratory Data Analysis and Visualization. We always reserve 1 section for our physics majors, and that could be anywhere from 20 to 25. I think in this fall, I started off with 20, but 2 students dropped it. And then I've had at most like 33 students spread across 2 sections. So there's a faculty member from CS who teaches the other sections, and then I teach one for our physics majors. And the way I approach it is that about half the class is spent learning Python. Most of the students have never programmed, although it's getting close to 50-50 where they've at least had some experience. And then half of the course is learning some statistics and really how to use the code for analysis. So I teach the students, what probably all of us do. You teach them about variables, loops, lists, conditionals, file IO. I teach them NumPy and Plotlib. I do not teach them pandas. And maybe I'll comment on this a little bit later, but I like pandas, I use pandas, but it hides a lot of the actual details that I think make it difficult if you're trying to teach some of the basics of programming. And I have to recognize that these physics majors are not all going to be data science majors, that they might be working on code that can't just be imported into a data file. And so I've made a conscious decision not to use pandas, although I think my colleague in CS introduces it. We use Colab notebooks. I have pre-recorded lectures on these different topics that the students watch. And then in class, we do a lot of hands-on work, and I communicate with the class through a Slack channel. Now, this approach to learning statistics used to be a bit less structured, but there's a new approach that I started using this last fall, which I'll comment on in a bit. All of the class is very, 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 very hands-on. They watch these lectures. They have to type out the code that they see me typing out, and they bring that and show me in class at the beginning of class. And then during class, they do a lot of work, either in groups or on their own, on applications of the concepts they've learned. And this is all informed by physics education research and all of the discussion about active learning, where you have the students really doing a lot of work. It's scaffolded to a point, but then at some point you kind of take the scaffolding apart and you try to get them to use it. And this really stuck with me when one of the students who was taking another course of mine said that when they took the other course, the other section of exploratory data analysis, they're like, oh, that class was actually easier because we would do things like learn about arrays, but we wouldn't actually have to know how to use them. And I'm paraphrasing a little bit, but her point was that in my classes, it's like, I would be like, okay, here's what it is, now go use it. And they struggled with that at times. Now, I want to mention that this is student perception. I think my colleague really was having them use it, but I might be just a little bit harsher or meaner, depending on which student you talk to. So I mentioned I started doing something different. So I had been introducing things like probability distribution functions, talking about the idea of fitting and hypothesis testing, kind of with my own notes and a little bit hand waving. But then the last summer, I saw someone on Twitter reference this book, The Art of Statistics by David Spiegelhalter, and said it was awesome. And I started reading it and I'm like, oh my gosh, this is fantastic. And so we used this book where they one class we would be learning Python, and in another class, because we met twice a week, we would discuss a chapter in the book. In this book, he talks about how to learn from data. He has all of these great anecdotes about catching a serial killer based on the data of when their patients, they were a doctor, when they were dying. They talked about looking at people who survived on the Titanic and who was lucky or unlucky, and some early research into like whether the height of a child is determined by the height of the mother or father. It's really good because he doesn't go into a lot of real details, but he introduces some of the concepts: interquartile range, differences between mode, median, and mean, and then it's in the context of somebody actually using the data to tell some story, some narrative, to solve some problem. It does take time out of class. I adopted this approach that I read about online called TQE, where students break up into groups and they write down their thoughts, their lingering questions, and their epiphanies based on their reading. I'm going to try to find a way to do this a little bit quicker, but it was able to generate a lot of discussion with the students. It was really interesting, some of the things that they picked up on. They really liked seeing this story. At the same time, some of the reviews at the end of class, some of the student evaluations felt that this book was actually, they weren't even sure why they were reading it. They're like, oh, I thought I was supposed to just learn programming. And I was like, well, no, even if you're a physics major, you've got to learn how to use your data to answer some questions. And that's what this whole book is about. So I've got to revisit, kind of reflect on how I did it last year. In this class, I also get to just do some fun programming stuff, some advertising, saying, hey, scientists do data science. So I have some data. It doesn't, if you're not familiar with the details, that's okay. But this is some data from the CMS experiment where you're actually discovering particles. You have two particles called muons that decay. You reconstruct a quantity called the invariant mass. You can see it in different charge distributions. And we do this to introduce the idea of masking arrays in NumPy. I do a similar thing with data from the Gaia telescope. And we look at different magnitudes of the stars. This region here, this kind of curve, is the stars in the Milky Way projected onto a particular coordinate system called right ascension and declination. And this also winds up being a good advertisement for students who may want to do research with some of the faculty, showing hey, you've learned this stuff as freshmen. Your first summer here, we've got students now that are doing research with some of the faculty because they can jump right in and start working with the data. The other class where you see this gets the idea, sorry, before I go into the other class, I just want to, this is actually the the big kind of reveal of this. So in this course, I've taught it now for 3 years, and I wanted to do this something kind of inquiry-based, and I was informed by some of the concepts that I'd kind of heard about from discussions from a educator, researcher at Cornell named Natasha Holmes. And she's been doing a lot of work on genphys labs. And she's like, look, if you can come up with a lab where you yourself do not know the answer, that's the best thing, because the students can't ask you. And then they're forced to actually do the work themselves. And so I leaned into this idea that every time I taught the class, we would have a different semester-long project where they would have to kind of like develop the skills and then at the end pull it all together. So the first year, one of our vice presidents at the school was part of this hunting and fishing club in the Adirondacks, this Chathamack club, and found all of these documents from like the 1920s and 1930s, all this correspondence, and a lot of it was like ordering fish for the lake to stock the lake. And he donated all of these papers, like a few hundred pages of it, to our library. And our library has a digital scholarship center, and they scanned them all. And so I was like, oh my gosh, I've got all these PDFs. And so I crowdsourced it to the students. So they had to do like, each of them would have to do like 10 or 20 letters. And they had to decide what they were going to record. And then eventually they decided on a schema, and they would record the date of the letter, whether or not it talked about fish, what type of fish it was. And so there was this massive spreadsheet at the end that they created over the course of the semester. And then their final project, I was like, just do something. I was like, do some visualization with the data. I'm like, I don't care what it is, just something valid. So some of them did these like time series of when letters were sent. If we had a whole other semester, we would try to like understand more about the structures, but they had to actually like at least make some comment about whatever plot they made about what it meant. And it was great. And a lot of the students hated it while they were doing it, because they're like reading all these letters and the spreadsheet wasn't filled out properly. And they had to do this data wrangling, which as an educator was exactly what I wanted. But they grumbled a little bit. But I'll come back to this in a second. And then the next year I taught the course, I'd heard about all of these terrible tragedies at the Santa Anita race course in California, where over the course of one racing season, there was about 20 or 30 injuries and the horses had to be put down. And I was like, I wonder if this is related to earthquakes in the area. And I was like, I don't know the answer. So over the course of the semester, we talked about, how to gather the data, which was not always publicly available. So we were scouring a bunch of different resources. We had to find out where to get earthquake data. And then again, we had this kind of common information that the students, compared the injury rates at not just Santa Anita, but to other tracks all over the US. We did not make a final determination, but it was a good semester-long project. And sometimes the students would give talks about earthquakes or horse racing, because again, the idea is not just to use a program. You got to figure out what it is, right? You've got to develop some domain knowledge. And then last year, we decided to incorporate more sports analytics. And so we talked about basketball. And at first, there was some discussion about whether or not this would be a gendered topic. The idea that maybe more men than women are interested in basketball. But it turned out that the majority of the students were not interested in and not familiar with basketball, whether they were male or female. And then the ones who were at least familiar with basketball was roughly 50-50. And the argument I made to the students was like, if you don't know anything about basketball, you're going to have a much better educational experience because you're coming in cold. And so Siena is a D1 school for basketball. It's a big deal at the college. And so we attended some practices and some games. Students had to learn about it. And then they collected their own data during one quarter of one of the games. And then they shared it. And again, they had to do some visualization of it. And they would come to me and they'd be like, well, what should I plot? And I was like, I don't know, do something. And I would, nudge them in the right direction. But by that point, they had the tools to like make plots and try to make some statement about, what it meant if there was like a whole bunch of rebounds or something like that. And this was really leaning into the idea of also data collection. What does it mean to collect your own data and then clean it? We also have a sophomore level course, Intro to Computational Physics. It's currently Python, but it used to be MATLAB. Again, it's mostly Colab and Jupyter. And the topics in this course, because they're sophomores, they don't have a lot of advanced physics knowledge yet, but we do finite difference integration. We do some Monte Carlo simulations with dice, birthdays, nuclear decays, some Fourier analysis. But the last 3 or 4 weeks, when they're working on their final project, I discuss computational tools and environments. And so I teach them the difference between version control, Git and GitHub. They all create an account on GitHub. They all edit some files and push them and pull them. I introduce some command line Linux. And because many of them have Windows machines, we used to use a product called Sage, but that became, you had to pay for it. So for the students who don't have Macs, I have them create an account either with Google Cloud Platform or AWS, the Amazon Web Service Cloud Shell. And so these sophomores come out of the class at least having created, a cloud-based account and logged into a cloud-based terminal through their browser, which I know that that's not data science on its own, but it's a tool that that they may wind up using. And then because I'm mean, I teach them a little bit of VI. They also learn a little bit about high performance computing. There's no homework associated, but I give a lecture about MPI, GPUs, and then Docker and Kubernetes. And I'm just about done here. The last thing I wanted to comment on is that we have a number of independent studies and capstone projects within physics. It doesn't have to be a physics project. And so if a student wants to do an independent study or capstone on something that's more data science adjacent, we are absolutely happy to engage with them. And so sometimes they may do some particle physics or astroanalysis, but I've had a number of students work on sports analytics with me. They've gone to, though they're not presented, at like the MIT Sloan Conference. And one student actually got invited to participate in the NBA hackathon at NBA headquarters in Secaucus, New Jersey, and work with some of their data. I've been working with another faculty member at Siena and a community partner since 2017, analyzing data on homelessness community throughout New York State. And I've got one student, we're looking at if we can use neural nets to extract symbolic mathematical information from data. So we're happy to engage the students in that. We also have some other activities on campus. So we have a newer-ish faculty, Kursad Tosin, in our math and statistics department. And last year, for the first time, we participated in this national competition called Data Fest. I mean, competition might not be the right word, but it's run by the American Statistical Association. There's a weekend where the students are given a data set. They have to analyze it over the weekend. We give them a bunch of food and pizza and drinks and stuff. It's open to anyone on campus, but about 40% of the students were physics majors this year, which we're really happy about. It was very open-ended. The data was super messy. But a lot of them said that they were actually ready for that because of the hell that I had put them through in some of my classes. So it was actually really exciting to see them all get super jazzed about participating in this hackathon. So I'm going to end here with kind of a series of questions, and maybe there's something for all to talk about. So at Siena, we're discussing this idea. Quite a few of our physics majors are getting the data science minor. But there's a discussion as to whether or not it's actually too many. The minor is very, very open-ended, and it's not clear that all of our students are really getting the skills that they want just by assembling a handful of these courses. It's supposed to be flexible, but some students might be getting this data science certification almost without really grokking more of what's behind it. I made this meme: one does not simply import pandas and call it data science. And again, I'm not throwing shade at anyone who uses pandas. I use pandas a lot, but anyways, I think you guys get what I'm saying. And so we've talked about a project-based course for the minor. Data science itself is working on a curriculum map, talking about what skills should a BS grad have, what courses reinforce those skills, and then where can our physics majors maybe drop in those courses. One discussion is a second semester of exploratory data analysis and visualization. The other one is maybe some one-credit modules that students can take. So a physics major who might take a one-credit class just on inference, or software carpentry, where we go a little bit more deeper into the Linux CLI and Git. because it's really just a cursory introduction. We've talked about doing a data assistance center, analogous to our writing assistance center, where we would have students staff the center and assist students on campus with their data analysis, maybe more independent studies, but we're not sure. I'm going to stop there, and I apologize for going a bit over the time that I said. Thank you.
Thank you very much. This is actually perfect. This leaves us a lot of time for Q&A and discussion with the audience. So I'm going to start off with some of my own questions and some of the questions on Slido, and then we may sort of open it up more broadly from there. Maybe I'll start with some questions for you, Matt, just because it's top of mind. The work on homelessness actually sounds pretty interesting. It's kind of interesting in that I also do some work with the city of DC on homelessness. I've talked with another physicist turned into data science who's doing work at Colorado. And so I guess that maybe leads to the question that was on Slido, in that both speakers mentioned personal and broader social issues. How do we leverage data science for teaching to better prepare students and make a better society? Do you think that this work on other projects helps in, or do you see things that we can do more in a physics context? And Amy, also feel free to answer this one.
So yeah, I'll give a brief background for the homelessness. This was actually partly motivated by a student that had been working with me, Sarah Mahar. She'd been doing some analysis with me on CMS, but she'd been starting to talk about the idea she wanted to do something that had more social impact. So I was just talking to people on campus. One of my colleagues, Ruth Castle, said she was starting to work with this group in Albany who had all this data on homelessness, but it hadn't really been analyzed. And so that was the seed for that. And that was actually inspired by a student who was like, I want to do something that has some social impact. Within the data science program, we've had some discussions about how to recruit more women and underrepresented minorities to the program. And there's been some discussion, and I'm a white man, so I don't know the answer to this, but my perception is that on average, women and students of color are more sensitive to issues and care, more passionate about issues of social change. And so if we can have kind of front and center these projects which are related to social change and social impact, not only does it just advertise that data science can do that, but we can draw them into the program and show them where these schools can have impact. And so on our end, we've just talked about, can we find projects that some of the faculty can start working on and then advertise this to the students? Because I think there is a community that wants to kind of like do more for society than measure the mass of the top quark to higher precision, which is really important. But I understand that it may not change everybody's life. But I'll pause there to listen to Amy's comments.
Amy, you're muted.
Okay, time to learn sign language. Okay, so I'd actually maybe like to ask the group this one, because I think that I definitely would second Matt's point about sort of project-centered work in classes. I think that's just a great way to sort of put the student in the driving seat and help them identify things that they're really passionate about and then be there to help them. I think that's a great method. So one of the things that I also kind of think about is sort of institutionally, right? How data science feels like it's relatively new. There are sort of data science centers and data science programs. And one of the things that's kind of been occurring to me is, how can we build equity into our promotion criteria and our tenure criteria as these new, as new centers and departments open up, and then also as we have more and more people from other disciplines participating in data science. So for example, I was talking with a colleague who is a statistical mathematician, and there's a society that actually has a carefully constructed sort of list, I guess, of and a list plus explanation of, when you are evaluating a statistical mathematician, these are the things that are really important to the field. And this is why. And so she was able to include that with her tenure packet and sort of say, look, reviewers, here are literal guidelines on how to evaluate me. And so I feel like something like that could be really powerful because, right, I think one of the goals in my mind is really encouraging students but also hiring more diverse faculty and supporting more diverse faculty. So just thinking through how we can do that with this relatively new, it's not all that new, right? But it's new in terms of the universities creating positions and people within universities identifying or being part of new centers. And so I'm just wondering if, is there something like that I'm not aware of in the data science world? Is there work like that? My instinct tells me that faculty representation is really important. Maybe that's wrong. I don't actually know much about the research in that area. So I'm just curious if anyone knows of sort of, institutional efforts like that.
If anyone has any answer to that, maybe post it in the chat. Also, I think that I do see a pretty interesting question in the chat itself. And I hope I don't slaughter your name too bad, Ali, but Ali Tabe, do you want to just ask your question? Do you want to unmute and ask it, or shall I read it?
I can ask it. So basically, some departments, especially undergraduate-based departments, they are like trained traditionally. So, and also their curriculum is more traditional computational physics. So I was just wondering, based on your experience, what's the best or shortcut way in order to incorporate these new techniques and these new methods?
I can jump in at least with our experience with that. Unless, well, I'll just tell you what happened, right? So, so we started kind of incorporating some of these newer techniques. Like I said, back in 2013, we had been teaching a lot of stuff more traditionally with MATLAB. And like I said, our students have been taking classes in the CS department in Java as their first course. And so within the department, we kind of had this discussion. And then we worked with our CS department, and I convinced isn't the right word, but we kind of negotiated with them to allow me to teach a course out of the CS department. So when I first taught this computational tools for physicists, it's listed as a CS course. And at that point, you're the instructor, and you can do what you want. Now, anybody who's a faculty member or has seen faculty members at any level, that there's a certain territorial aspect that comes on. In the beginning, it wasn't a smooth discussion, but we worked together. And so I'm not saying that this is the best way. But what we did is basically offer to put in the person power to create the course that we needed for our students. Like I said, it took some time, and someone had to take on that workload, and it was a ton of work in the beginning, but at least that was a bit easier than telling them, hey, you have to teach this the way we want you to, because someone else will always balk at that. And so for us, it was really just saying, hey, we will take on this workload for our students. And then we kind of did what we wanted to, where we were really informed by the research that the faculty were doing. And then we said, well, look, what do the courses need to have in them so that a student could come out of freshman or sophomore year and contribute. So that was our experience. I don't know if it's the best one, but that was what worked for us.
Yeah, I don't have a whole lot to add to this, because I think this is right. I think that our department really sort of like there aren't curriculum guidelines for classes. And so it's very much an environment where historically, teachers have taught their material and that's it. And there's no sort of broader departmental discussion. I'm not saying that that's the best situation. And I think that can make it really hard to do what you're suggesting, right? Like making sort of an overarching change that affects all the students. So I would say that my experience is somewhat limited to, as an individual instructor, what do I need to adopt new practices or new material in a class? And for that, available material that's findable has been absolutely critical. So when I first started teaching physics, those physics tutorials from the University of Washington, like saved me. I don't know if I would have made it through the first year as a professor without those. Anyway, so I feel like the easier it is to hand someone material and say, you know, this exists, I think that really improves the chances that that's usable. But right, like at some point you have to sort of, someone has to be willing to try that new material, and how you do that, I suspect, changes from department to department.
Hopefully some of the modules that our fellows are developing as part of this project will be useful in that regard. But it does sort of lead us to one of the other questions on the Slido, which is, you know, is there any movement towards having a standardized list of learning objectives? You know, what skills and proficiencies should our students have by the time that they graduate? And this seems to be like something that Matt's department has been grappling with in terms of, at least on the data science side, you know, like what do you think that they should come out with at the end? What informs that? You know, how is that journey going?
Right. So for the curriculum map, which I started, you know, I'm sure, you know, this summer we're going to get down into the weeds, and I'm sure there's going to be some things that are common, right? I would like the students to see Python and R at some point, right? So I would like them to see that. And then it's a question of like, should they see the central limit theorem, right? Like how deeply should I go into the central limit theorem, which I would claim a data scientist should know. And I think we'll have some other faculty are like, oh, that's just details. You know, everything's a Gaussian. It's totally fine. But I think that that's an important discussion. Should our students see interquartile range, which is used like a lot in, you know, statistics and data science. But as a physicist, I almost never use IQR. I almost never do any sort of analysis with outliers. But other faculty might. It would be great. Yeah, I mean, I totally agree with you. It would be great if there was some like central location we should go to. You know, and I think so much of what's been happening over the last 10 years with data science has been at the master's level. I feel like it's relatively new for undergrads to be exposed to these ideas. So I think this is a really active topic of discussion. You know, if I write down my dream list of what I would want a BS student to come out with, I don't think I could do it in 4 years. You know, so at that point, it becomes a little bit of triage. You know, like I want them to see regression, but do I want them to see like all the aspects of machine learning? Probably not in a time. So I don't know. I think within our group, it's going to be quite a topic of active discussion once we get down to the details of what we would expect the students to see.
Amy, do you want to comment?
Yeah, I just want to say I'm not aware of anything, so I would be really interested in hearing if anyone is aware of anything. So in physics, the only thing that I'm aware of is that, for example, for the labs, you know, what should students get out of labs? That is it the APS? I think it's the APS that did this. They released a report where they had a list of sample objectives for the end of lab courses for students. And what their suggestion was that every department sort of go through those sample objectives and decide what was most important to them. So I think that, you know, right, like engineering has this long history of departments getting accreditation, and physics has a long history of, I feel like, kind of being like, don't tell me what to do. And so I feel like it would be, I could see maybe something like that from the data science community, right? Some kind of report that's like, yeah, physics does actively resist accreditation. It's really tough because, well, anyway, okay, so that's a whole other thing, right? But I think, yeah, I think that what I could maybe see happening is having like a national data science organization put some kind of report together that's like, these are recommended proficiencies, and then departments deciding on an individual level what proficiencies they're going to focus on, and, you know, publishing those. So yeah, I don't know if there's anything, you know, any kind of data science accreditation I'm not aware of any, but I'd be really curious to know
For data
where this is
science,
going.
for data science itself, there's sort of 2+1 at this moment. I mean, there's a National Academies report for just pure data science, not data science in the context of physics, but pure data science. There's a National Academies report. There's also one by Talitha Washington, who's now at Atlantic University, that sort of outlines what, that consortium thought would be good to go into the undergraduate curriculum for data scientists. For the EU, there is the Edison framework as well. And then there's also a group called the Academic Data Exchange that is trying to provide sort of a professionalization and merger of these, of these different frameworks. And so, at least for just pure data science, there's work on this. Data science in the context of physics is a little different because, okay, we have a whole major of our own, and then we're also trying to incorporate data science. And so maybe that leads to sort of the next question, which is, so Amy, you spent, which is, part of one of the ones on Slido, is you spent a lot of time talking about getting computation into the classroom. And this is sort of like a prereq for some of the data science, right? If somebody, if we have students and they don't speak Python, it's kind of hard to, go from there to, okay, can we teach them about a random forest or something, much less, some of the other work with statistics. So, have you thought about, sort of what, how the work that you're doing on the computation side sort of prepares the students for data science down the road? And, Matt, if you want to talk a little bit to this as well, then that would be great. But
Yeah,
Amy.
yeah. So I would say that you're absolutely right. The work that I do, especially in my introductory physics classes, is very much more focused on computation. And in particular, when students are interested in going deeper into it, we tend not to point them into the direction of data, which would be more of, data science, but we tend to point them into the direction of uncertainty estimation and sort of finite element analysis, uncertainty, like what's the error on if you make this approximation, and what's the error if you make this approximation. Right. So I would definitely classify that as computation. And I see another question is does computation differ from data science? And I don't know, but I feel like I would call that kind of thing computation, just because it's not using a data set exactly. Yeah, so I think that what you described about sort of the fundamental skills required, that's really how I see this preparing them for data science in the future. So especially for the students that don't have acts like that haven't done any programming whatsoever, it's really interesting. It's really interesting the kind of errors that we see. There's like a whole class of errors that has to do with, oh, I have to spell it exactly the same. For the computer to realize that I'm talking about that variable, that the case has to match of all the letters, right? So there's kind of this you have to type the word exactly the way it wants you to type the word. Anyway, so I think, but I think that it's really just kind of that fundamental computer skills of understanding, how do you read code? What matters when you are typing code? That's important. But at least in my class, we really don't delve into the data part of data science. We really kind of restrict ourselves to I would say purely computational. The one aspect where it maybe starts getting into something that's really directly relevant for data science is sometimes students will be like, can I plot this? And that's great, right? So, but we treat that as a sort of an additional thing that we talk with students who specifically raise that, and we don't specifically work on plotting. I think that if we were to do specific work on plotting, that would probably do a better job of preparing them for data science. So that's something we should consider. Anyway, I don't know if that quite answers your question, but yeah, absolutely, computational and the foundational skills, I think, is what we help students with currently.
And Matt?
Yeah, so I agree with everything Amy said, and it's going to sound like I'm disagreeing. So let me preface this, right? So So I'm a total computer nerd, and I love learning how to write my bash scripts better, and I like will just play around on computing. So I love computing, and I think it's super important. But I firmly believe that it's important to make a distinction between that and data science, right? That computation is this tool that we can use to answer many problems, especially nowadays in the era of big data and big data sets. And to be a data scientist, you really do have to know computation. And so this is where I 100% agree with Amy that all of these things that we're teaching in our classes are preparing them and giving them the foundational tools to be able to go and do data science. Data science to me is really about trying to answer a question and also trying to come up with the question that you're asking, right? So in physics, sometimes the questions are easy. Is dark matter a particle, or is it not real, and stuff like that. But then once you get into the subtleties of how you answer that and how you collect the data, and then how you interpret the data, that to me, I see is where the data science mindset, data science mindset comes in. And I fear that sometimes, and I fall into this myself, I am kind of like, if I know Python and pandas, I'm a data scientist, and I have to check myself and be like, no. A lot of data science is coming up with the question, figuring out how to collect that data, and then going through that, analyzing that data. And that book, The Art of Statistics, talks about this. The computation is really, really good to kind of test these ideas. So in class, we did a Monte Carlo simulation of uncertainties. And it was this idea that you're measuring the time it takes something to fall 1 meter. You measure the distance that it falls for 1 meter, and then you estimate the acceleration due to gravity. And when I did this, I would generate a bunch of like random measurements for the time and a bunch of random measurements for the distance, and then calculate the acceleration. And I expected to get a nice Gaussian for my measurements, and it was not Gaussian. And I spent forever trying to figure this out on my simulation. I'm like, why? It's supposed to be Gaussian. My uncertainty should be Gaussian. But it's not, because the time that you measure goes into the equation as 1/t squared. Anyways, I won't go into the details, but it was really interesting how this simulation showed me something that deviates from this simple assumption that everything is Gaussian. And I feel like that's where you start to get in a little bit more of this idea of data science, where you kind of try to think a little bit more deeply about what your results are. You can argue that that's just physics. That's just what we should be doing anyways. But I feel like, for me, I try to emphasize to the students that the computation is a tool to solve a problem, whether it's physics or data science. And I often have to keep reminding myself of that, because I could program all day just for fun, but that's still not data science. So again, I'm not disagreeing with anything Amy said, but I'm emphasizing it's this foundation tools to solve these other things.
Maybe if I could, would it be okay, William, if I said a little bit more on this, because this,
sure.
Okay, because this is actually, so I think that, this idea of, right, what do we use? I like, the other background information that you need to know about me is that I grew up on Terminator 2. So this question of, right, what is our relationship with computers, and how do we incorporate them into our world in a way that helps us, is something constantly on my mind. But this idea of, right, so I would say that, what I'm doing, I would say, is definitely computation. But I think what it really does is it gives students another way to look at the problem and evaluate whether or not they think the answer that they're getting is reasonable. And I think that it's a way that comes a bit more from them than from the back of the book. And so I think in that sense, it sort of supports that sense-making, question-asking, understanding piece that's so important in so many different fields, but certainly also data science. So, right. So, and I'll give an example of this. So I had a group of students who had been really excited about, for every homework set, one of the students in particular made her Python programs, and she thought that was really cool. And so, so they came to sort of this conceptual problem. And they were really struggling with agreeing within their group on what the correct answer to a conceptual problem was. And so the student, and it was a magnetism problem, so it had the cross product, which is why they were all they were all forgetting different parts of the cross product. And so then they were all disagreeing, and they were all kind of right. So finally, this girl was like, I know this is a conceptual problem, but what if we put numbers in? And I built it in, because I already have this program that can calculate something similar. So I think we should put numbers in and then use my program and see who's right. And so this group was, and it was a pretty, like, the setup was like, they actually broke it into, it was like a kind of complex current distribution, and they had to estimate, the magnetic field at a particular location and what direction it was going to be. So they actually ended up doing like a really thorough job of like breaking it. Like they worked for like 3 hours on this problem. And they ended up breaking it into like really small elements, and they programmed it all. And they got an answer that they really didn't expect. And so then they took over the entire, they kind of were like, we have a problem and we need to present it to the entire class because this is a really serious issue and we don't know what's going on. And so they each presented their argument about what they thought the answer should be. And then the woman who had written the code walked through her code, and she was like, it's not wrong. Like we checked it in this way, we checked it in that way, we checked it for this case, and it gives exactly the same answer that the book does. I mean, it was, they just did a really fantastic job. And so then they presented this to the class, and the entire class discussed it. And then one person in the class said, I think that you're forgetting the divide by r squared, and I think that you're forgetting the sine theta. And I think if you put that information in, then that would all be consistent with what the program is saying. And anyway, so I think that sort of like additional check and sense making is a really important, can be a really valuable and important part of the computation. So basically what Matt said. But
and I'll just add another perspective, right? Where so Amy, I completely agree with you that computation in physics is incredibly useful, right? I mean, that if you look at, say, E&M, or you look at quantum mechanics, or even if you look at a general relativity course, you can model things and gain intuition in a way that is difficult to achieve with just equations alone. And that this is incredibly valuable and a good chance to sort of develop your intuition more strongly. But I think that there is a difference between just computation and data science that's come up with, sort of came out in some of the memes that Matt brought up. And there is sort of a general idea that computation is one of the pillars of data science. I mean, without computation, you can't do data science. Statistics also enter into this. I like to say that physicists are great at probability, but only some are good at statistics. And that's another big challenge, is trying to get statistics into the physics curriculum. There will be a talk on that at the workshop that we're running. Shameless plug. But sort of data science is sort of broader than computation. But I guess I could ask for like one last comment on this before moving on, which is, Matt, you've done all of these memes. Does that do anything for the students in terms of trying to define this difference between data science or computation? Or is that more for like us as like instructors?
There was a couple Twitter threads about a year or two ago with some like high school teachers that like asked they like taught something about like the 1972 election, and then they had their students write memes about them. And it's interesting because the students, the memes that they would write gave you some insight into what they learned. Right now, I am not saying that we convert everything to memes. It's just that, right? So when I taught the students about like editors and operating systems, their only homework assignment was to create a meme that like referenced, what we learned. And so it was just for fun. It was something, and it was interesting because some of them did a little bit of research and a little bit of digging. And were able to like make jokes about VI and Emacs that were a little bit beyond what I did in the class. And so, it was just something that's in my head, and it's a way kind of for me, it's a tool for me to kind of poke fun at myself, take the air out of myself a little bit with some of this stuff, especially when you're talking about, well, which approach is better, Python or R, VI or Emacs, Debian or Ubuntu or something like that. But it's really no more than just like a lever arm to kind of like have a little bit of fun with this. And sometimes it gets students that might have been a little bit more shy or a little bit more hesitant. It gives them something that they can jump into that they feel a little bit of comfort level with.
So one question that I have for both of you that also comes from the Slido is, where do your students land after graduation? If they don't wander off to physics grad school, then, where do they wander off to? And, does this, inclusion of data science or computation, does that aid them, in sort of like their next step if it's not physics grad school?
I can maybe just briefly talk about this, and then I'm really curious to hear Matt's answer since he has you guys have a data science curriculum. So we've just started, we've just gotten a data science major approved at our institution, but students have sort of informally done data science through research. And what we see is that a lot of the students who have data science experience in research and also have a physics major but no other major have a really hard time finding jobs. So I don't know if that's other people's experience or if that's just our department, but without some kind of credential, that I feel like local industry doesn't know how to make sense of a physics credential, and plus data science experience. So we've had students who've gotten jobs as research assistants and in sort of the academic system with their data science skills, but they've had a hard time getting jobs in industry unless they already have a computer science degree. So that's kind of what we've seen, and that's really tough because they have the skills, but it's not obvious to the places that they're applying. So anyway, I'm curious what other people's experience is.
Yeah, so at our school, most of our physics majors tend to want to pursue more engineering type jobs. We have a couple of more industrial like employers in the area, or they go work for the state. And this is where our applied physics major has been coming. And then we have a few students that'll go on to grad school. A couple students, more than a couple that have gone on to like medical physics, some students. But in terms of the data science side, right, the first few students that were doing kind of data science intensive stuff wound up pursuing master's programs. And then after the master's programs, they got jobs. But we've had a couple of others that have graduated with their BS and then gone to work in the healthcare industry doing data science. We have a couple big hospitals in the area. One student who had done the data science work with me, he just got a job with The Athletic, which is a sports publication, an online sports publication, doing data analysis for them. I 100% agree with Amy. There's a ton of places, though, that don't know what to do with a physics major. And so we've had students that have really had to work hard to like emphasize either the research that they did that was data intensive, or now that many of them are getting data science minors. So some of them will get a job at, like, we have a big pharmaceutical company in the area called Regeneron. And we've had students that have gone there and they're doing like quality control. So like a lot of data analysis, it might not be advertised as a data scientist job per se, but it has, they know that you're at least aware of what a database is. You can work with a spreadsheet. And obviously there's more than that. But even then, the students kind of have to work hard to pitch themselves. And then we've started to make some outreach to like the New York State government. Sometimes they have internships that we've been working to try to get our students involved in. But that's where students have been going, either to some industrial company where they do something along the lines of like quality control that has a data component, but it's not as much, except for a handful of students that have gone on and got their masters, or some of these other kind of like special case rock stars. I don't know that they've been just like falling into the data science jobs, but we've only been graduating like, I don't know, 4, 5, maybe 8 data science majors a year. And then again, the majority of the physics majors are get the minor. Some do a dual major, but.
Okay, yeah, I think that that is really good to know. Well, we're down to 5 minutes. Before I go into some of the remaining Slido questions, does anyone in the audience want to raise their hand to ask a final closeout question? Just throwing that out there for a minute. Well, Matt has his own hand raised.
Yeah, I just want to kind of comment on, I think I was going to raise it if you hadn't earlier, this like question about like statistics, like I think, the discussion about computation, I could talk about that for like all week if we wanted to. But I've been thinking a lot more the last like year or so about what statistics do we want our physics majors to know? What methods of inference, like we never teach our students regression. We might teach them line fitting, maximum likelihood. But in the data science worlds, it's things like regression and that type of language. And so I think if this discussion continues forward, if there was some sort of coalescence around a set of skills, I am fascinated to see what people think about statistics, that people should learn. How deeply do we go into like Bayesian versus frequentist and stuff? And that I don't have an answer for that. I'm just kind of seeding it if anybody else has a comment or question in the last couple minutes.
Well, I have strong opinions, but let's see what the audience says. You raised a question for which I think that there was only one answer, but
is that the Bayesian?
Of course, right?
Yeah, we just don't teach the frequentist at all, and
yeah,
right.
we just move on from there, right? But others may choose to differ. Yeah, so I think that that is a worthwhile discussion to think about, like how much statistics and how to include it within the physics curriculum. Also, the approach that we've been taking, with our fellows is to develop modules that can integrate into the curriculum, so that, somebody could look it up and say, oh yeah, like I want to throw in, like this module on deep learning and it fits into classical mechanics, so that's the approach that we've been taking. But trying to figure out how to do that for statistics is pretty hard because there are, dependencies, right? Like whereas there are some things that you can do without as much of a dependency tree behind it. Okay, so I don't see other questions. I mean, I think that the statistics question is maybe a long one that we can continue on Slack. I think that would be great in the DesiCop channel. So anybody who is not on our Slack, please join our Slack, and hopefully we can post a link for that. But prosaic question was environments for Python, collab versus local. I mean, Matt already said that, okay, he's just moved to the collab. Our modules will also be collab because then we just don't have to deal with the dependency issues. Amy, are you using collab or using local or?
Yeah, we use Trinket, but it's like collab. Sometimes students have their own environments already set up, and of course we support them with that. But yeah, no, I think that, right, the real question is, I would always prefer to have the environment set up in a central location and then have the students access it so that they don't have to do that setup on their computer. And that's what I push in my own research for setting up analysis environments for my scientific research. And I just think there's just no question. The issue is, do the students have the internet access? It works great unless they don't have internet access. In Denver, the baseline internet is pretty decent, but in other parts of the country, I think it's a different story. And certainly in different parts of the Front Range, it's a different story. So anyway, so I feel like that's the answer that I want. And I think that the other thing that we need as part of that is like national fiber infrastructure. So anyway, so national fiber infrastructure, please, so that we can stop provisioning individual computers, because that is a good way to go insane.
Agreed. Okay, so I believe that we're at 2:30, which is our planned stopping time. We managed to answer think the vast majority of the questions. I think Matt and Amy, if you're not on our Slack, if you don't mind joining, then it would be great if you could. If people have additional questions, then maybe they could seek you out there, and we'll sort of bring this to a close. Thanks again to Matt and Amy for all of your time and sharing what you've learned with us. We really appreciate it. All right.
Thank you for the time.
Yes, thank you guys so much.
Okay, so I think we can stop with the recording.
Amy, that was great. I'm glad we got to like kind of interface face to face after past email.